let me start by thanking the organizers for inviting me to give a talk in this very nice meeting. The title of my talk today is Exact Fluctuating Hydrodynamics of the Scaled Light-Heavy Model. So I've put this scaled word in brackets, and I'll try to explain why we need to scale these the rates of this particular model. And this work has been done in collaboration with the graduate student Shilpa Prakash and my colleague Mustansir Barma at TIFR Hyderabad. So let me begin by explaining what model we are looking at. So there is a class of systems where we have fluctuating local drives, that is driven systems at the local level, and some of them break detailed balance at the microscopic scale, and these give rise to very interesting phenomena, non-equilibrium phenomena. And even though many models are built using very simple rules on the lattice, an exact determination of their hydrodynamics is quite hard, and many talks in this conference have been regarding these hydrodynamics and how to describe them. And so I will describe another model in which we have tried to determine the hydrodynamics exactly. So these systems which have fluctuating local drives have actually been very studied very much in the recent past because of their connection with active particle systems, and several key questions about the dynamics of these systems still remain open, although much has already been understood. So in that context, one-dimensional models where particles are coupled to fluctuating surfaces have been quite useful to characterize many behaviors, including clustering and a lot of non-equilibrium phases. And this is really a precursor to the kind of models that people study with active particles. So let me describe this model. It began with a study by Lahiri and Ramaswamy. Shriram is in the audience. It's called the light-heavy model. This was initially proposed to understand clustering in sedimentation, but is quite a useful model to study many different physical phenomena. It consists of two species of particles, light and heavy. They are interacting with the fluctuating membrane, and it can be described by the following simple objects on a lattice. There are tilts, which are described by these up and down tilts, and there are particles, which are two species, basically light and heavy. And you can think of it as tilts interspersed between particles, or you can think of it as these tilts forming a hill and a valley, and particles being on the surface. So it's just for some notational convenience, we can call these the light and heavy particles as by some Ising variable sigma, and the up and down tilts by some Ising variable tau. So the microscopic evolution rules of this model are as follows. Particles preferentially roll downhill. So if there's a particle on a slope, it will prefer to go and roll downhill with some biased rate, A. So half plus A in this direction and half minus A in the reverse direction. So it's biased towards rolling downhill. So this is how particles are channelized by the surface, but the surface itself can also be affected by the particle. So if you have a heavy particle, it will try to pull a hill into a valley, so it's naturally sort of moving downwards. So if there's a particle in a heavy particle in the top of a hill, it will try to make it into a valley with some preferential rate B. And similarly, a light particle will try to pull the membrane up. So you can think of them as a bubble and particles. So this is a particle, this is a bubble that likes to move up, and that has a preferential rate B prime. So these are the rules of this model, and just by these very simple rules of particles interacting with surfaces, you can create very rich phase diagram, and using these three rates, A, B, and B prime, you can have disordered phase where you have no order in the hills or the valleys, or in the particles there's no clustering. You can also have very strong phase separation when B and B prime are both positive. So this is known as strong phase separation. And you can also have different phases depending on B and B prime, which is infinitesimal currents or finite currents. And there's a very interesting line here where you see something known as fluctuation dominated phase ordering. So this has been studied in great detail by many people in this audience, including Dibyendu, Shriram, Mustansir, and many collaborators. And this phase diagram has been quite well understood, I would say. You can also characterize these different phases by looking at the coarsening behavior of these phases in time. So in the strong phase separation region, if you find an appropriate length scale to measure, the strong phase separation region shows logarithmic growth in the length scale, whereas if you look at the other phases, they have some other distinct exponents that can characterize these different phases. So this has been the sort of summary of the light heavy model up till now with the parameters A, B and B prime that have been done in the literature. So we defined the following model. It's a scaled version of this model where we define the rates. So the bias rates are scaled by the system size. So if A is some finite number order 1 alpha divided by L, similarly B is some finite number divided by L, and B prime is some number divided by L. So we take this phase diagram that I just showed you, which has a lot of many different phases that are that can be observed, and then through some analytic arguments as well as simulations, we find that many of the phases that we find that we had seen in the unscaled model actually disappear, and we have a slightly different phase diagram where you have, depending on B and B prime, you have a phase separated region and a disordered phase. So all these strong phase separation and these other phases are not present in this model, but it still has a critical line that is that separates the disordered phase from the phase separated region. So the main goal of defining this model is to be able to write down exact hydrodynamics equations. So the previous model, which is not scaled, has been studied in detail, but through phenomenological approaches where hydrodynamics has been written down, but writing fluctuating hydrodynamics has been tough. So we decided to study this model in order to do that. So to do this, we use the general action formulation, which has already been described in quite some detail in the previous talk by Tridib. We take these two species of particles and we basically define particle currents and tilt currents, and then we write this path integral for the currents, which can then be used, that can be exactly computed using many different formulations, including the ones by Doi and Pellitti, and we come up with this action that describes the full evolution of this system. So using the action of this model, you can then just compute the fluctuating hydrodynamics by looking at the Euler-Lagrange equations, and we get the following equation. So at this point, I'll pause a little bit and describe that these basically have a diffusive behavior along with some advection, and then we have two types of noise. And here, so this is the noise that is associated with the rho field. So let me just clarify. Rho is basically describing the particles, and M is describing the tilts, right? So we have basically two coupled fields which have these diffusive and advective terms as well as noise. And then one can, using this action, also derive the exact correlations between the noise, and there are some Gaussian noise with some dependence on the density. So the density correlations of the noise has this behavior, whereas the MM correlations or the tilt correlations, the fluctuations in the tilt correlations have this following behavior. What is important to note here is that the density and the tilt noise are not correlated. So that comes in because of the particular nature of this model, and these noiseless equations that I've written down here without these two terms, which are the noise, can also be derived using phenomenological approaches, and many studies have done that, including this one that I've quoted here. So at this point, I would like to compare and contrast with a particular model that has been quite well studied in the literature now in the last few years. That is a model of active particles where the same techniques can be used to compute the fluctuating hydrodynamics of active particles. And this is sort of a subject that has, of course, sparked a lot of interest. So this following model that was defined a few years ago allowed one to do that. And so the model is very similar to the model that I'm talking about. It has two species of particles, some of them moving towards the right and some of them moving towards the left. They are active because they're able to change their direction. So the plus particles which are biased towards the right can turn into a minus particle which is biased towards the left with some rate gamma. And you also allow diffusive hopping between sites, which basically allows you to either exchange particles or move one unit to the right or the left with some rate b. what is important to note here is that the bias, that is the bias towards the right or the bias towards the left, has been scaled by the system size lambda by L. Similarly, the rate at which a plus particle can turn into a minus particle is scaled by the system size as gamma by L squared. All of this is done so that when you write down the full hydrodynamic equation for such a model, all these terms come at an equal footing in the hydrodynamic equation. And so one could try to understand why this model is related to the previous light-heavy model that I'm talking about. So let me just go back and show you the picture of the light-heavy model. So you have two species of particles being advected by the surface. So if you are on a slope in the right direction, so all the particles that are there are moving preferentially to the right, and particles to the on a slope which is on an upslope are preferentially moving towards the left. And this model, of course, is also contains within it the ASEP, because if there's just a uniform slope, then all the particles are biased towards one side. So now due to the fluctuations in the surface, some of the plus particles can become minus particles. And so in this case, if you don't consider the surface, that's like a hidden variable, then you'll have it looks very much like an active lattice gas, where particles can either go to the right or the left, bias to the right or the left, and change their properties as well. Whether they are biased towards the right or the left can be changed due to the fluctuations of the surface. So now one can do the exact same treatment in this fluctuating hydrodynamics treatment for this particular model, and it's been done in some studies before. And they see a very interesting phase diagram where, depending on the activity and the density, you can have something which has been claimed to be a motility-induced phase separation critical point with the diverging correlation length. What is very important to note in this particular model is that this diffusive exchange is necessary to see this hydrodynamics correctly. Some studies by Gregory and co-authors have shown that if you don't have this diffusive exchange, you don't see the correct hydrodynamics, or the fluctuating hydrodynamics derivations do not describe what you see in this model. So this diffusive exchange is very important. And then recently, some of the authors, including Sanjeev, Abhishek, Tridib, and so on, were able to come up with a model where they allowed diffusive exchange to happen by creating two lanes. And so particles can hop between these two lanes and be able to exchange. So this diffusive exchange is very important in this particular model. It turns out that in the light-heavy model that we are studying, that is naturally already there, because we don't have this particular way of turning a plus particle into minus particle, but I'd be happy to discuss that more in the questions. So fluctuating hydrodynamics of active lattice gases was done recently by Lecomte and co-authors. What they were able to show is that you have very similar equations that we wrote, diffusive equations with some advective terms, but now you have this conservative noise, which is for the rho field and the m field. So let's just go back. The rho and m in this case are defined as plus and plus minus particles. But you have an extra type of noise, which is known as this, which is a non-conservative noise, which is associated with the flipping process. So the plus particles being converted into the minus particles give you this extra type of noise. And then again, using the action, you can compute the correlations between the noise. An important thing to note is that the rho and m noise here have a different correlation than what we saw in the light-heavy model. They actually are non-zero. And similarly, you can actually write down the correlations between this Poissonian noise, because it is related only to the density, because it's the flipping term. But what is very interesting to note is that there was already a model in the literature some years ago known as the ABC model, which has very similar behavior and also has these correlations of the noise are exactly the same in that model as well, because the model can almost exactly be mapped onto this active lattice gas. So this fluctuating hydrodynamics of the ABC model can also be done, which we have done, and also has been done by other authors. In this case, you have basically three species of particles, A and B and C, and they are biased to move using these rules. So if an A is to the left of a B, it exchanges with some preferential rate Q, and similarly with B and C and A. And in this case, in order to derive these exact hydrodynamics, one has to scale the rates which you can do in this particular way, where you have n is the system size, and you can scale q, and with some beta order 1 parameter, you can scale the rates. Once you've scaled it, you can write down in exactly the same manner this fluctuating hydrodynamics. But here, one has to note that both of these noises are conservative, and using the action, you can then compute the correlations of this noise. This is exactly the same correlations of the noise as you see in the active lattice gas that I just showed. So with all of this setup, does this hydrodynamics work? So in the rest of the talk, I will just show you some convincing evidence that it does. So we evolve the density fields in this model, and starting with some density profile, we can allow the system to evolve. And so this is the noiseless hydrodynamics that I'm talking about. So this is averaged over many different configurations, and you see that the evolution of the theory, which is this, which are the solid lines, matches very well with the evolution of the actual numerical simulations. And then you can check the error, and it does seem to go down with some slow convergence as you increase the system size. Then the natural question one would ask with the fluctuating hydrodynamics approach is that is the computation of correlation functions. One of them is the static correlation function that you can derive. So if you remember, there was 3 rates, A, B, and B prime, which we were scaled. So you got alpha, beta, and beta prime. And in the phase diagram, you actually have a critical point at beta equal to minus beta prime. So if you want to look slightly away from the critical point, you can just look at some parameter delta, which tells you that you can go away from the critical point by some amount delta, and then you can just linearize the hydrodynamics equations, but keeping the noise terms there. And within this linearized hydrodynamic equation, knowing the correlations between the noise, one can derive the density correlation function, the MM correlation function, and the cross correlation function as well. Again, just done using the correlations between the noise and the linearized equations. So these are our predictions for the correlation function, very similar to what has been predicted for the active lattice gas. And then we just check that these correlation functions work. So as you go closer and closer to the critical point, so this is going closer to the critical point, you see that this correlation length actually changes. There's an exponential decay that we predict, and then you have this correlation length that changes. Similarly, you can have correlations in M, and it works quite well with simulations. The fluctuating hydrodynamics approach that we have used actually predicts a diverging correlation length. So if I just go back to the active lattice gas, there was a diverging correlation length here in this phase diagram, whereas we are predicting that in this phase diagram, this entire line has a diverging correlation length. So there are some quantitative differences between these two models, which remains to be studied further. So we have the following prediction, which we are testing, but what remains to be seen is how good these predictions are. So if you compare with simulations at some values of these A, B, and B prime, which are quite far away from the critical line, you actually see that the density correlation function and the MM correlation function work extremely well, so, as does the cross correlation function. But as you approach the critical line, the fluctuations become larger and larger, and then the correlation function predictions no longer are very good. So this is something that can be explained in multiple ways. Either the fluctuating hydrodynamics is not working at this point, or the linearization of these equations is not working very well. So we have been studying this particular aspect in more detail, but as you get closer to the critical line, as was also the case with the active lattice gas, the correlation functions are not very well described by the linearized fluctuating hydrodynamics equations. So with that, let me just sort of wrap up. The correlation functions can also be used to compute this through the entire phase space. And there's one very special point in this phase diagram where actually, if you look at the correlation function, the 2-point correlations actually vanish in the disordered phase. And it turns out that that particular point is a very special point known as, that we have studied in the past, which is a bunch-wise balance point, where the rates exactly cancel out in order for the currents in configuration space to be zero, incoming and outgoing currents. I will be happy to talk about this later in detail. But this point actually shows up. So in our fluctuating hydrodynamics equations, we have the incoming rates and outgoing rates for every configuration. The probability currents from a group of configurations actually balance out and can be uniquely identified with another group of configurations that balance out this current, and so you have zero probability current in configuration space at this point, and that is a special point where you have 2a plus b prime is equal to 0, and that shows up as in the fluctuating hydrodynamics equations with zero correlations. So we are trying to understand this slightly better. So let me conclude by just saying that what I showed was the static correlation functions, but since the fluctuating hydrodynamics has within it the full dynamical correlation function, one can of course study that. And so what you can start with is a density inhomogeneity and study the relaxation of this density inhomogeneity with time, and we have at some particular Fourier mode, we chose to study this relaxation, and the linearized hydrodynamics equations predicts this kind of behavior, whereas actually from simulations we see not an exponential decay. So we can also show that along with the nonlinear terms in the fluctuating hydrodynamics equations, they do describe this relaxation quite well, but this is just a few Fourier modes. We have to check the full Fourier space to see whether all the modes are well described, and so this is something that is ongoing, where we are trying to understand what are the corrections and the nonlinear corrections to the linearized fluctuating hydrodynamics, which are already predicted, and whether the action really predicts them correctly. So with that, let me summarize. We've derived the exact fluctuating hydrodynamics of the scaled light-heavy model. So the light-heavy model is very well studied, and so we scaled the rates by the system size in order to be able to write down hydrodynamics equations where all the rates are at an equal footing. It would be interesting to study the critical line itself. That remains to be seen whether or not this approach will work. And one really interesting question is whether at the critical point, the correlation functions display a power law. This is something that fluctuating hydrodynamics cannot predict, because it predicts an exponential decay no matter what near the critical point. So getting a power law correlation function near the critical point would be interesting, and also would be interesting to understand what correction terms are required in the fluctuating hydrodynamics. We are of course studying the nonlinear terms near the critical point. And finally, I would just like to point out that since this approach of calculating these fluctuating hydrodynamics is quite popular these days, many other models on the lattice can also be studied, and some of these are being studied by us as well. There are some very interesting evolutionary models that are generalizations of the ASEP and so on that can also be studied in this approach, which is what we are doing. And with that, I'm happy to take questions.
Long live India and France friendship.